All right, so it's now my pleasure to introduce David Bercovici for the Birch lecture, and I'll just tell you a little bit about David as well. So Dave got his PhD at UCLA back in 1989, and then spent time as a postdoc at the good old Woods Hole Oceanographic Institution before moving on as a professor at the University of Hawaii. Since 2001, he's taken up residence as a professor at Yale, which included an extremely productive stint as the department chair from 2006 to 2012. And it's fun to see the new activity since being relieved of that duty, which is coming on these days. So we know Dave from a lot of the great work that he's done, and he really uses a novel application of geophysical fluid mechanics, or fluid dynamics, and continuum mechanics to study a wide range of geological and geophysical processes. And throughout his career, he's just made super contributions to the fields of mantle convection and plume dynamics. And perhaps, maybe the biggest impact he's had is on his novel application and development of damage theory to provide a great link between mantle convection and the unique plate tectonic style we see on Earth. He's followed up on that work using multi-phase physics and kind of new applications of the damage theory to do a lot of other really neat stuff, looking at volcanic processes and lava flow processes and melt migration and a lot of other really great problems. I remember kind of when I first met Dave, it was in the kind of a setting like the Gordon Conference, and what really struck me about him was there was this super great articulate guy who was so enthusiastic about his science and so willing to share it with everyone in both informal and formal settings, talking to students and postdocs as well as colleagues. And that spirit, I think, really shines through when you look at all the great collaborators and students and postdocs that he's mentored over the years. And it's really, really great to see that, and he's a great leader in showing that way of making successful science. So without further ado on those great words for David, I give you David Bercovici and the Birch lecture.
Thanks, Greg.
All right, thanks a lot, Greg.
Don't lose that.
All right, I promise not to lose that. Well, first, thank you, Greg. I'm losing my voice a little bit, but with this lapel mic, hopefully you'll be fine. I'm told not to cross the white line here. So thank you, Greg, and thank you also to the Tectonics section for inviting me to give this talk. I think, in fact, there must be some tradition with this lecture that there should be, it's appropriate to give a word about the great Francis Birch. And given the subject matter of this talk, probably that word is irony, because Francis Birch was, in fact, a staunch opponent of continental drift. Okay. However, of course, his seminal paper in 1952, JGR, actually really established the structure of the mantle and the core, to the extent that we pretty much use that same structure even to this day when we're looking at models of mantle convection. And also, this paper is quite famous for the fact that he slipped a joke in here, which probably gives you words of wisdom, even as you're listening to this talk, that whenever we're dealing with any research regarding the interior of the Earth, you have to translate certain things. As he says, certain things undergo a high-pressure polymorph, so things that we would call certain really mean dubious, okay, and undoubtedly means perhaps, and you can read the rest, okay, especially for those in core dynamics, okay. So, regardless of that, every day, effectively, we are reminded of the existence of plate tectonics, and even more so every week as the accumulation of earthquakes builds up, and every month, and this is in fact just a month and a day and a week before yesterday, okay, which is easily plotted from the USGS, just reminding us plate tectonics is always happening, okay, and in fact, of course, we can see it even on the human scale, okay, when it leads to these major catastrophes, for example, of course, in the Tohoku earthquake in 2011. I'm not going to review all the theory of plate tectonics. What this talk is about is my biased view of the cause for plate tectonics and the origin of it. Okay, and as Greg said, some applications of damage theory, which I'm going to torture you with a little bit at some point. Okay, but of course, plate tectonics, briefly stated, is that the Earth's crust and lithosphere is broken up into these puzzle pieces that move with respect to each other. Okay, that's sort of the statement of the theory of plate tectonics. That then, of course, have where they run into each other, they're convergent. Where they move away from each other, there's divergence. Where they slide by each other, they're transform faults or strike slip margins. Okay, it's about as much as I'm going to say. Okay, for that. Of course, the importance of plate tectonics actually really does go beyond what we consider the textbook version of the importance of plate tectonics. What we're usually taught, of course, is this is where earthquakes and volcanoes occur. And of course, it is extremely important. It's not just looking at seismic distributions or seismicity, but it's also the fact that the plate tectonic theory tells us the type of earthquakes and volcanoes that occur. It tells us whether there's giant earthquakes or small earthquakes, explosive eruptions or oozing eruptions. Okay, so it's very important for that aspect too. Okay, but it also goes beyond that, sort of the textbook definition, maybe this isn't textbooks now, okay, that plate tectonics controls the evolution of the planet, okay, not only in how the planet interior cools, but also the evolution of the Earth's climate. And I often like to annoy my climate science colleagues by telling them that the most important part of climate change is plate tectonics, okay? In fact, what we usually, without this is a whole topic unto itself, okay? But what we usually say is that the major reservoir of CO2 on the planet is luckily not in the atmosphere, it's at the bottom of the ocean in carbonates. Otherwise, we would have about 60 bars of CO2 in the atmosphere, and we would not be all that unlike Venus. But instead, because of the constant exposure of minerals and rocks from plate tectonic cycling, they scrub out the CO2 and dump it on the seafloor as carbonates, and these are eventually subducted back into subduction zones and leaked back slowly into the atmosphere. But the major reservoir sits mostly at the bottom of the ocean. But the important part, of course, is the negative feedback between climate and weathering, and that if climate gets warmer, it enhances the weathering rate, which sucks CO2 out of the system and cools things off again. And likewise, if there's a climate cooling event. Okay, so it's an important negative feedback stabilizer for Earth's climate over tens and hundreds of millions of years that allow, of course, life to develop into complex forms like us. So this is always our big question, okay? Is the Earth really unique? And as far as we know in our own solar system, it appears to be. Maybe Mars may have had plate tectonics a long time ago, but it appears at the moment Earth seems to be the only planet with plate tectonics, liquid water, a temperate climate, and life, okay? Which are all probably dependent on each other. So understanding why that is and the conditions for which a planet develops plate tectonics becomes an important part, not just for understanding our planet, but for other planets as well. Okay? And this has become particularly important, especially for astronomers. There are many people in the audience who have also worked on this problem. Since, of course, the mid-1990s, there's now up to about 1,800 confirmed exoplanets. Another 3,000 or so, or they're called candidates from the Kepler mission. Only about 300 or so are terrestrial or super-Earth. Okay, and the big interest is whether or not they sit in the habitable zone. Okay, and part of that discussion of the habitability on these planets, okay, is whether or not they have the conditions for plate tectonics that would then keep a stable climate or a temperate climate. And so the issue of whether or not these planets can sustain plate tectonics becomes an important part of the entire exploration for exoplanets. So being able to generalize to say something about other planets becomes very important. So to dive into the physics, or to dive into the processes that we think about in terms of how plate tectonics arises, okay, on a planet that's convecting, I'd like to start at the beginning, okay? In my biased view. We're skipping 9 billion years of the history of the universe, okay, for the interest of time. And, okay, but so we started at about 4.6 billion years ago when we wind up forming the planet, and a lot of the accretionary heat from collisions, okay, and from the formation of the planet, okay, is stored as, the conversion of kinetic energy to heat, that's then stored as primordial heat that continues to leak out to this day. Okay, and most of the heat that's leaking out from the planet as the planet is just slowly dying to space, okay, the heat that is leaking out of the planet, a very large fraction of it is from this primordial heat stored from its accretion. It's losing heat that slowly. And a large fraction of it, probably more than half, is from this primordial heat, probably less than half is from heat from radioactive decay, okay, of elements like uranium and thorium that provide a heat source as well. And this is the fuel for plate tectonic activity, and it's actually a very small source of energy. It's not that big. When you compare it to what the sunlight that we receive every day, it's about 4,000 times smaller, okay? Okay, so, but this very weak heat source can be focused by mantle convection, okay, into narrow currents of upwellings and downwellings, okay, and to provide sort of the driving force for for a lot of geological activity. Of course, we're talking about mantle convection, okay, which is many of you in this audience are people involved with mantle convection, as my old advisor Jerry Schubert and I have been for many years. Of course, the mantle is this thick layer of rock between the crust and the core, and it convects very slowly. When we say convection, we just mean the hot stuff rises, the cold stuff falls, and the mantle rock near the surface is cooled and gets heavy and sinks. Okay? And that's probably one of the more important aspects of even discussing convection. It's also, of course, incredibly slow. All right? We know, of course, it's just tectonic speeds of 1 to 10 centimeters a year, but it governs how fast the planet cools, it governs how geology progresses, and so forth. Okay? But most importantly, the Earth is probably the only planet we know of so far where this convection reaches the surface. In other words, where the circulation of the mantle actually interacts with the surface by dumping mantle rocks effectively on the surface and then ingesting surface material back into the mantle itself. Okay, and no other planet we know of yet really does that. Okay. Now, I can say right away, okay, before even going into anything complicated, a very important part of the connection between convection and plate tectonics is just the existence and presence of subducting slabs, where plates are heavy and they're cold and they're heavy and they sink. Okay, because in a mantle that has this amount of heat stored in it from primordial heat from accretion or from radiogenic decay is going to be dominated by downwellings, by cold downwellings, in a sense that these downwellings are cooling the mantle off the way you would drop ice cubes in hot tea. Okay. And so this Earth-like internal heating is very typically, or it's typified by being dominated by cold downwellings, okay, which is what we think the Earth is also dominated by cold downwellings. Not just, you know, in model world, but also we can look in tomography and see the very distinct signature of slabs. Whether they go to the bottom of the mantle or not, or get stalled is not the point. We can actually see them, okay, quite clearly. We also notice that there's the correlation between the slab pull force, okay, and plate velocity. It tends to show that the fastest plates, you know, always have a slab connected to them. This is from a classic paper from Forsyth and Nieda from a long time ago, 1975. And also, we can very easily show that the mantle is cooled by just dropping slabs into it like ice cubes. Okay. Hopefully, I'm not going so fast that we'll have 30 minutes of questions, okay? So, the plate generation problem goes a little bit beyond this issue of just slabs because we have to actually explain the other plate boundaries as well. Okay, how do we wind up getting to these other plate boundaries, such as strike-slip margins, passive spreading centers, things like this? Okay, so there are various questions, and these are ones that I'm going to try to address today. How does plate tectonics arise from a convecting mantle? That's the big one. Okay, why Earth and not Venus? What can we say? What sort of physics or what sort of laws can we infer that we can generalize to say something about the conditions for plate tectonics on other planets, especially when we're looking for habitable planets in other solar systems, okay? And then there's other major questions like how did plate tectonics even start, okay? When did it start and how did it start? And then continuing, how did it evolve and reorganize through time? So these are things I hope to touch on. Again, this is going to be my biased view, okay? So there are lots of people that have worked on this, but you're getting my take, okay? So one thing we know in mantle convection, the convecting mantle is just slow. As I said, it's very slow, 1 to 10 centimeters a year. It doesn't have a magnetic field to make it complicated. It doesn't have rotation to make it complicated. It isn't even turbulent. It's just slow. Okay? But one of the biggest complexities with mantle convection is how the rocks that are flowing deform. Okay? When you apply some stress to them, how do they actually deform? Okay? And in the area of the mantle that we're most worried about, they undergo this type of deformation called creep. Okay? Where, for example, there's dislocation creep, again, sort of at these mantle temperatures and stresses, where you're sliding along what's a dislocation or a missing row in a crystal lattice. You're sliding along to relieve stress. Okay. Otherwise, you can have diffusion creep. okay? It's slightly lower stresses, ostensibly, but in which, as you're squeezing something, you're forcing atoms to basically diffuse away from where you're compressing it towards tension, relieving stress, and the diffusion occurs either through grains or along grain boundaries, which means that if you have small grains, okay, you have smaller grains to diffuse across, or many more grain boundaries and pathways that you can move through, okay? So that implies that the smaller the grains are, the easier it is to drive this diffusion. So the real logical laws, try to keep my equations to a minimum here, okay? You may not agree with what that minimum means, but, okay. For example, in dislocation creep, we will have a strain rate. We actually define things. Strain rate, okay, that is dependent upon a stress to some power. It's called non-Newtonian because it's nonlinear. It's usually a power of 3. Okay, and it usually means that as something flows and deforms, it gets weaker and softer. Okay, so this is typical of dislocation creep. Diffusion creep is linearly dependent on stress. Strain rate and stress are, you know, in a Newtonian sense, we're linearly dependent on each other, but it's strongly dependent on the grain size. The smaller the grain are, the easier it is to deform, okay? Because the easier it is to derive diffusion from compression to tension. Okay, but both these are very strongly temperature dependent, meaning that for the cold lithosphere near the top of the mantle, it tends to be very stiff intrinsically. Okay, and this has often caused a problem in mantle convection, in that when we consider, you know, the convective states of the mantle, sort of the Rayleigh number versus the contrast between the coldest and the warmest rock, the contrast in viscosity between coldest and warmest rock, there's this region called stagnant lid, meaning that the lithosphere is so cold and stiff it will not move, and convection just goes on underneath it. Okay? And where we would map the Earth turns out to be right in the stagnant lid regime, okay? Which would imply the Earth should have no plate tectonics, according to some of these basic ideas. Okay, so plate generation mechanisms effectively try to undo that problem, try to loosen up the lithosphere and undo that stagnant lid, okay, and allow plate boundaries to form and to soften up and form. Okay, so, but most terrestrial planets are in the stagnant lid regime that we know of. Not many, our data set is tiny, but what we know of, okay, that they're in the stagnant lid regime. But the Earth, we think, has these self-softening feedbacks, okay, that allow plate boundaries to develop. Okay, and in particular, for example, generically speaking, the deformation would cause the material to soften, and by softening, the deformation focuses on that soft zone, which makes it deform faster, which makes it soften faster, which makes it focus on that deformation, and you get this positive feedback that leads to a thing called shear localization. Okay? A simple example is if I'm heating something up by friction, it will get softer as it gets warmer, and I will wind up focusing deformation on the soft zone. Okay, this would, in principle, allow a convecting mantle to generate strong, broad plates because I will localize deformation to narrow bands, and those narrow bands would look like weak plate boundaries. Okay, so we'd have narrow, weak plate boundaries, and we would like them to last, that is, not vanish, because we want to inherit them later, for example, to use them for initiating, for example, new subduction zones. Otherwise, it's very hard to get a new subduction zone to form in this stiff, stagnant lid. Okay? And then we also would like to generate this thing called localized strike slip shear. Okay, we'll get to why that is a little bit later, okay, if I don't go too slowly. So there are some very sophisticated, elegant models that look at convection in these sort of self-softening rheologies. They're very similar to this dislocation creep where, you know, strain rate depends on stress to a power, and it gets softer the more you deform it. And sometimes they're called plastic yielding, meaning they'll get softer once they exceed, the stress exceeds a certain yield, a yield stress. They will tend to generate very nice looking plates with, you know, weak boundaries. This is a viscosity field with weak boundaries, and they actually develop very plate-like looking flows. Okay, and so they're incredibly useful for actually trying to run convection with a sort of instantaneous plate-like flow. Okay, however, they have one little problem, which is that those plate boundaries vanish as soon as they stop deforming. Okay, so there's no way of inheriting them. There's no sutures, there's no dormant weak zones that perhaps can be inherited to form a new subduction zone. Okay, because again, there's no history to them. They're basically instantaneous. Okay, so to try to go deeper into the problem, I often say we have to go from the global scale to the grain scale, and this actually works amazingly. Okay. Okay, and rather cheesy way, but I'm not that good at that stuff. Okay, so so we go from the global scale to the grain scale. What I really mean is to kind of focus on what these things called myelinites. And there are various kinds of myelinites, and this is a peridotitic myelinite, really from the mantle. And a myelinite is a rock, okay, that is found, is pervasive in deformation belts and a lot of plate boundaries, okay, that is in regions of, like I said, very high deformation. It's characterized by very high degrees of deformation and shear, and also associated with greatly reduced grains, okay, or grain size. So the grain size tends to be anomalously small. Okay, and I believe that these are, as many people that have looked at this problem think, that these may be an important clue to how plates are generated, or plate boundaries are generated, okay, because this process of the development of myelinites does occur in sort of the deeper lithosphere. Okay, so these are probably nature's important clue to us about how things are working, or not, okay, but we'll follow that anyway. All right, this is not an intermission, okay. Okay, this is just to try to understand something about grain scale processes. We actually like to consider the simple example of foam in the beer. Okay, and you can consider this later, but you'll have to let your beer sit there for such a long time, it'll get warm, it'll be awful. Okay, that foam, okay, any kind, will actually undergo coarsening. Okay, simple foam will undergo coarsening from small bubbles to big bubbles. And the broad sense is basically just going from a lower energy state where there's all the surface tension that's in between all these little bubbles on the membrane between the bubbles is going away, okay, is being reduced. So it's going to a lower energy state by getting rid of the surface energy going to bigger bubbles. But in effect, the big bubbles are eating the small bubbles because the small bubbles have a very high surface tension in them. They have very high curvature. They're being squeezed by the surface tension. So the pressure on them is high, and that high pressure squeezes them into the bigger bubbles. Okay, so in a sense, that's how the big bubbles eat the small bubbles, okay, because the small bubbles are being squeezed. Well, grains and rocks effectively do the same thing, okay, more or less, okay? I mean, it's more complicated, but the idea is the same, that you're going to a lower surface energy state by going from small grains to big grains. And in fact, if I take a rock with grains in it and let it sit there, not at room temperature, but at some higher temperature, you know, something more characteristic of sort of the mid-lithosphere, 900 degrees or so, that the grains will eventually grow. And in fact, in a laboratory experiment, very nice ones done by this Haraga's group in Japan, you know, these grains will grow over about 50 hours, 2 days, and you'll see this grain growth occur. Okay, they start with very small grains, but you can actually see it occur. Well, as the grains grow, this material would ostensibly get stiffer because the grains are bigger. It's harder for it to creep, at least certainly by diffusion creep, okay, because as grains are bigger, diffusion creep is less efficient. Okay, and it would become stronger, okay, as the grains would wind up growing. But with deformation, in principle, with deformation and damage, which I'll define better in a bit, if you want, you can think in terms of dislocations in the minerals that wind up propagating and connecting to make new grain boundaries, okay, that the grain size could be reduced, okay? And this is the hope to how do you wind up generating this myelinite that I showed you a picture of a minute ago. The grain size could be reduced, and if the grains are reduced, okay, the rock would soften because it's in diffusion creep, it's an efficient form of flowing if the grains are very small, and the rocks would soften and you get a positive feedback because if you soften them and you deform them faster, okay, then you wind up crushing or grinding the grains down further, which will make it softer, which will continue to focus deformation. So it's that feedback we look for to cause narrow boundaries in this localization. And this may be appropriate for this deep lithospheric mechanism, you know, below the brittle ductile zone, okay, in the deeper, strong, cold ductile region of the lithosphere. And it also appears to be evident in the myelinites that we see pervasively in these regions of high deformation. But there is always this problem. It's a classic problem that people worrying about myelinites have been thinking about, is that in a single material like an olivine, this mechanism feedback just doesn't work. Because in a single phase, the grain reduction should only occur in dislocation creep, when dislocations are propagating around, connecting up to make new grain boundaries and make the grains smaller. Okay? But while it's in dislocation creep and the grains are reducing, it doesn't care, the viscosity doesn't care about the grain size. So it's not softening at all as the grains get smaller. Likewise, if you get into the diffusion creep in small grains, it may become softer as if the grains are small, but the grains won't shrink, okay? They'll only grow because there's no dislocations. This has often been the quandary of this problem, that the grains will all wind up migrating to this saddle or this line between dislocation and diffusion creep. Okay? So there shouldn't be, in principle, any feedback mechanism that we would see generating something like these myelinites. Okay? Well, real rocks, of course, are not just simple olivines, they're mixtures. At least, in my simple-minded view, they're mixtures in like a mantle peridotite, okay, of olivine and pyroxene. I mean, various forms of pyroxene, okay, but I'll keep it simple. My olivine and pyroxenes are either green or blue, okay. So the grain growth, in this particular case, in a mixed system, tends to be blocked, okay? Tends to be blocked as a grain, as a big olivine tries to grow and it runs into a grain of pyroxene, its growth is blocked because if it tries to engulf that other grain, okay, it goes to more surface energy by becoming more distorted, okay? Having more protrusions in it as it tries to engulf this other grain, which is a higher energy state, which is not preferred, so it will shut down grain growth, and this is a thing called Zener pinning, okay? If we damage the system by deformation, okay, this is sort of where the theory my colleague Yannick Ricard and I have been chasing for a while. If we damage the system, not only can we perhaps drive some dislocations in the grains, but we'll also sharpen, okay, the interface, say, between the gray and the white from a nice drawing from a paper by Phil Skemmer and Greg Hirth and others from a while back. We'll damage the interface, or we'll stretch and mix and contort the interface between them and cause smaller pinning bodies. Okay, I'll get into this better explanation in a minute. So we drive smaller pinning bodies that hold the grains in smaller sizes, or even drive them to smaller sizes into diffusion creep that allows us feedback. Okay, so I'm basically damaging pinning bodies that then drive the grains to smaller sizes, and then they're softer because they are in a small grain size state that allows this diffusion creep to occur. Okay, we're getting into a lot of details, so we should move a little faster. Okay, but the point is that the damage and the softening can coexist. Okay, what do I really mean by this pinning effect and grain growth? So this is my version of a grain, the spherical cow, the spherical grain. Okay, we have a large olivine pseudograin, okay, surrounded by these small grains. The high curvature of the small grains squeezes them and effectively causes a larger pressure, really chemical potential energy that drives mass from small grains to big grains. The big grains eat the small grains, okay, and you have grain growth. Okay. If I jam pinning bodies, like these little pyroxenes, onto the boundary of the larger grain, and it tends to preferentially distort the bigger grain because it fits on it, okay, you can cause so much distortion and sort of higher surface energy on it that you can reverse the direction of flow, because this is basically making the big grain look like a smaller grain by creating so much curvature in it, it's being squeezed, okay, more, and drive the direction of flow in the opposite direction, or stop it altogether. If you stop it altogether, that's called pinning, okay, where you have shut down any grain growth whatsoever. Okay, and that's a very simple version of things. What do I mean by damage? Okay, when I say damage in the broad sort of energetic sense, okay, just in terms of transferring energy, that's really what damage theories really mean, is that if I'm going from a big grain and breaking it into smaller grains, I have to create more surface energy, okay, and to get that more surface energy associated with all these extra surfaces, okay, I need some energy, okay, and that is only going to come from the work that I do to grind it down, okay, so it's almost like Griffith's crack theory. I need to have some work to create new surfaces. Okay, so the damage comes from the deformational work, right? And that's what we mean by damage. If we include the pinning bodies, in fact, we have a bit of a head start. This thing is so distorted, this grain is so distorted, that it has a head start in terms of going from high energy to perhaps a higher energy, but it's already got a head start, so it's easier to damage. In that sense, pinning actually helps out with damage. To develop some physics for this, we actually have to consider, it's not so horrible, it's only a few equations that I'll show you in a second, but we have to consider all the interfaces, for example, between the olivines, okay, these are now purple olivines and blue pyroxenes, okay, at least the pyroxenes are still blue, okay, and so in this case, we're looking at the olivine surface. We really mean the grain boundaries of the olivine, the grain boundaries of the pyroxene, and then the interface between the two of them, and we need some evolution for all of these, okay? And yes, there's going to be a few equations, but we'll try to make it as painless as possible, okay? In this particular case, when we're looking at the evolution of the roughness of the interface, or the radius of curvature of the interface, we're really looking at the competition between healing or coarsening, just standard as you let it sit, okay? You'll go to a lower energy state and it will coarsen, okay? So there's coarsening competing with damage, which is driven by work, okay? These are stress, okay? That is basically trying to grind down the interface or stretch it and rend it and give it a higher curvature. Okay. Likewise, we have very similar laws for the grain sizes. There's this I means either olivine or pyroxene for either phase. Similarly, there's a competition between coarsening and the damage. Okay. But they're coupled with it by this thing called the Zener pinning factor. And the Zener pinning factor is something that drops out rather nicely from all the thermodynamics that you had to grind through, but it basically states that for very small grains, maybe separated by large smooth interface, you will get really no pinning. Okay, so in that sense, this ratio would be very small, and the z is 1, and it just undergoes normal coarsening. But if the pinning bodies or the radius of curvature of the interface is very small, so the pinning bodies are small like the little blue blobs I showed before, okay, then it will cause more pinning. If this is 0, it's pinned, means you shut down grain growth, okay, and you can even make it go a little negative to start driving grain reduction. Okay. We then take this grain size and put it into a rheological law, strain rate versus stress, but it's dependent on grain size and can be non-linearly dependent on stress. So it combines both dislocation creep and diffusion creep, but done in such a way that whichever mechanism allows the fastest deformation is the one that dominates. Whichever one releases stress fastest winds up dominating. And these, by sort of going through the physics at this grain scale, these various constants are related to laboratory experiments for coarsening. I mean, we could always do better, okay, but at least it's based upon some measured values. Okay, that's kind of it for most of those equations. So let's apply this, okay? Doing okay on time. Let's apply this to some flow calculations. We can now take those few equations I showed, and we can put them into some simple flow calculations. And one very basic example I'll go through pretty quickly is this idea of how do we wind up generating, okay, this thing called the strike-slip flow field of the Earth. If we separate the Earth's, I'm going to need to go back. Excuse me. Thank you. Okay, I can't go back myself. Okay, it's like I can't walk backwards. Okay, all right. We can separate the Earth's velocity field into divergence, which is associated with spreading centers and subduction zones, and what I call a toroidal field or vorticity, which is associated with strike-slip motion, say along the San Andreas Fault, or for example, where the Indian and the Pacific Plate are moving 90 degrees to each other. Okay, so you can get this strike-slip vorticity. Okay, but it's very hard to explain this from a convective standpoint because it just involves side-to-side motion or spinning motion like in a hurricane. It doesn't transport heat out of the mantle. Convection doesn't directly drive it. And you have to explain it by coupling it to this flow field, okay, by a bunch of complex rheology. Okay? So the idea is that in a source sink model, if I were to drive lithospheric flow with a source of mass, say at the mid-ocean ridge, to a sink of mass at a subduction zone in some simple 2D flow calculation, what rheology would let me recover, okay, the strike-slip vorticity field? This is a very standard test that I've done, I hate to admit how many times, okay? But for example, we can take a much, much simpler point of view for this. This is the postage stamp version of plate tectonics, in which we drive material from a source to a sink, and if it's a constant viscosity, there's nothing interesting about it. Okay, the flow field is not going to look very plate-like. In fact, it looks like magnetic field lines, okay, going from one pole to the other. Okay, that just gives you one standard. But if we then, for example, apply it to something with dislocation creep, okay, with a power law of about 3, okay, meaning strain rate depends on stress cubed, okay, then we can wind up getting some bands of strike-slip motion, a slightly blockier looking plate-like flow field, and weakness, or that is low viscosity wrapping around a stronger plate. Okay, so it doesn't look quite like a plate boundary, but at least looks like a weak zone wrapping around a strong core of a plate. If we actually try this with this damage physics, but without the pinning, okay, without the pinning, we don't drive the system into diffusion creep, and therefore we don't get any feedback. And in that case, it looks very much like the above case with a little bit of improvement. But with the pinning, we get very profound localization of strike-slip margins. We get these very intense bands of vorticity that look like strike-slip faults almost in a way, a much more plate-like blocky looking flow and a very weak zone wrapping around the core of a plate. Okay, so that's a real simple example. Okay, let's do something more interesting. Okay, is to try to address the real question. Okay, why and how did plates actually emerge? Okay, in the early Earth. And one aspect that I want to talk about, okay, before jumping into more, is actually some work that my former graduate student Brad Foley did, okay, and looking at applying some of this damage physics in convection models, but actually thermochemical convection models, to ask the question, what happened directly after the magma ocean froze? And one idea from Lindy Elkins-Stanton, who is one of our collaborators, is that during crystallization of the magma ocean, you wind up having a chemically unstable stratification of heavy material at the top, lighter material at the bottom, which then caused, as soon as once crystallization was more or less finished, to cause a very rapid overturn, and then sometime later a build up to normal mantle convection, normal thermal convection, but it may have taken a long time. So the question is, how long did it take to go from that very rapid quick overturn where you're flipping over this chemically unstably stratified mantle right after the freezing of the magma ocean to something that looks like convection? And is that convection plate-like? Okay, do we actually get something like subduction out of it? Okay, and so Brad did these very nice calculations, starting off, for example, with the chemical stratification, that's C for chemistry, where it's heavy on top, light on the bottom. Okay, that red really means high. Okay, temperature is hotter on the bottom, and we wind up causing a very rapid overturn, chemical overturn that is very abrupt. Okay, and then convection starts in, and you have a normal thermal convection, but you wind up, because of the high viscosity in the top, you wind up retaining some heavy chemical components in the top as well. It doesn't get flushed out with everything else, okay, up to the bottom of the mantle. And that's actually quite important, because if we combine that with the damage physics, eventually that heavy lithosphere that's retained founders, drops off and sinks into the mantle, and starts off something that looks like subduction, and sort of like, it's a 2D model, so it's hard to say whether it's plate tectonics or not, but it's at least you get surface motion, okay? And so in that sense, the combination of retaining some chemically heavy material on the surface with damage allows you to say that convection with plate, something like a plate-like motion, or at least surface motion, initiates, and it can initiate actually reasonably quickly after the in the Hadean. And for example, this plot shows this lag between the first overturn and that sort of normal convective overturn with the plate foundering, or the surface foundering into the mantle. And we can ask, how fast does it occur? Well, with significant chemical contrast and with significant damage, it can occur in a few million years or 10 million years, depending upon how hot this mantle is. So in other words, we can get that lag between the first chemical overturn and something that looks like subduction to be reasonably fast. Well, that may correspond with evidence for the presence of something like subduction and formation of continental crust in, more than 4 billion years ago. Okay, as we know, there's this a lot of literature on zircons. Of course, a lot of these zircons for this argument come from one area in Jack Hills, Australia. But the idea is that these zircons are present in granites, and therefore granites, since we mostly think of as being formed in subduction zones, okay, that this is a sign that there was something like subduction developing continental crust really early on, more than 4 billion years ago. Further work by Mark Harrison's group sort of suggesting that these things even formed in sort of a colder subduction-like mantle, okay, by doing thermobarometry on these to suggest, again, that there was something like subduction occurring really early on, okay. And so that would sort of go along with the idea that maybe we could get subduction to happen pretty quickly, or something like it, okay. However, there's also this other line of evidence, of many more lines of evidence, okay, of geological evidence that suggests that plate tectonics wasn't really in full activity till about 3 billion years ago, okay, not 4 billion years ago. And in various recent work by Steve Shirey implies, for example, diamond inclusions don't start to show the sign of subduction, of eclogite in them, till about 3 billion years ago or so, okay. So there seems to be this 1 billion year strange lag of some sort between the first proto-subduction indicated by those zircons to other stuff. So, no, not doing so bad. Okay. This is also summarized very nicely by a nice paper by Kent Condy and Alfred Kroner, discussing all the various geological evidence for when did plate tectonics start. And they summarize it very nicely in their abstract that plate tectonics, okay, probably started, was widespread by about 2.7 billion years ago or so, okay? But as he states, it's unlikely that it was on Earth as a single global event, that it probably started locally and spread, okay, throughout the Archean. And that's something that will they'll chase with this, with the damage physics and some of the ideas that I've already shown you to try to address this model in a very simple-minded way. Okay, that we start off with the assumption that proto-subduction that we already talked about, this early subduction, was intermittent and time-dependent. Okay, that with this, in the hotter mantle, perhaps a thicker crust, it was harder for it to subduct. So it may have just subducted and then dropped off. Okay, and oftentimes we see that subduction tends to be in these systems very, very chaotic anyway. So we start off with the idea that subduction was moving around and chaotic or intermittent, okay, but that the damage formed by these proto-subduction zones would have been retained. In other words, once we get some sort of flow under, by a subduction zone, then the damage that it causes to the surface would last. And as a subduction zone vanished to move somewhere else, that damage zone, okay, would be kept and inherited to be used as a passive boundary somewhere else. Okay, and then the subduction zone would move, and we would wind up keep inheriting these damage zones to eventually form, okay, fully formed plates. And the idea is that this could occur easily within about 1 billion years. Okay, so I have this very simple model. There's big parts of hand of God to this, but other than the damage physics, which is to state that we have a 2D type lithosphere driven by a low pressure zone just sucking the lithosphere into the mantle. And we just impose that one pressure low, and it drives lithospheric flow, which causes a weak zone. Okay, and then we move the subduction zone, hand of Dave. Okay, move it around, and we see if we inherit that. Okay, to make up a passive margin. Okay, and so because of the damage physics that we've developed, you can retain these weak zones, okay, over some finite period. We'll see it does depend upon the surface conditions. All right, because these postage stamp models look so boring, I decided to wrap them on a sphere and make a movie out of them. Okay, not that they're that much extra scientific content, but it looks slick. Right? Okay, so let's see if this works. It doesn't just kill everything in the room. All the lights go out and everything. Okay, all right, so here we go. So we start off and see that a subduction zone first formed, and you can see I'm moving the subduction zone around. Okay, I'm going to give it one nice little spin so you can see it all. Okay, and in the end we find that there is the subduction zone driven by this low pressure zone. Down here there is a passive spreading center. Okay, there's some oblique spreading centers off to the side. You can see there are these bands of strike slip vorticity, and the viscosity field, okay, is forming a very narrow band that wraps around looking like a weak plate boundary. Okay, I know that looks great, but it's probably more meaningful to look at the actual calculation, okay, done on this postage stamp version. Okay, and as we kind of migrate the subduction zone around, we keep inheriting the last low viscosity zone from here, okay, to develop a passive margin, and then in the end we wind up having a single subduction zone, low pressure zone, driving a convergence zone. There is a passive divergence zone, passive strike slip margins, a plate-like type velocity field, and it is just being driven by one subduction zone. Okay? And if we actually look at the divergence, this is S, okay, it's always being built and collapsed every time I move this subduction zone around, but the vorticity, the strike slip field is growing and growing and growing and actually becoming more intense, okay, and even at the end, okay, it's actually becoming more focused even though nothing is driving it directly. So again, we have one subduction zone directly driving convergence, but a passive spreading center and two passive strike slip margins, okay, to give you this. And it's all done by this, inheriting these damage zones as you move this around. Of course, that's done in this sort of orthogonal, moving the subduction zones around, nucleating them off the last subduction zone, just so you can very clearly delineate the different types of plate boundaries. We can do this with sort of a non-orthogonal, non-90-degree rotation, something maybe, for example, like going to the Emperor Hawaiian Bend. So if we have plate motion being driven by subduction, say, for example, along the Aleutians originally, okay, forcing plate motion, more to the north, and then we rotate it again. Again, there's nothing fancy about the rotation. We can see that we inherit some extra complexity, but most interestingly is that the original configuration of the plate is kept. Okay, and that we wind up with oblique spreading centers, okay, and oblique subduction zones, and oblique strike slip margins that all have some mix of divergence and strike slip motion to them. Okay, and if we actually blow up what this looks like in comparison, it's a stretch to compare it to the actual Earth, but it's surprising how much that simple calculation winds up giving you a lot of these same features of oblique spreading, okay, and oblique strike slip margins. And if you really want to push the interpretation, okay, this extra complexity by this superposition of these subduction zones, okay, going from one to the next has left something, a little chunk that looks something like the Philippine plate, but I didn't say that. Okay, but now what about Venus? What about other planets? Okay, so we can do the exact same example, but we'll go to a higher surface temperature, which means a hot surface means greater healing, faster healing, and lower damage. And in this case, we start off with something driving subduction, but as the subduction zone moves around, you can see it bopping around here. Okay, as it moves around, we're not inheriting any weak zones of significance. There's some wisps here of weak zones, okay, but nothing gets inherited to develop a passive margin, or a passive boundary, like a strike slip margin or a divergent field. And the vorticity field you see is almost non-existent. Okay, for the interest of time, I'll just whip through that fast. Okay, it's the same calculation. Again, you see you're mostly just dominated by subduction. Okay, but very little vorticity, and the vorticity never seems to build up in that case. Okay, so can we say something? Can we sort of generalize from a lot of this? It's just one example, okay, of how we think of plate tectonics perhaps initiating in this very simple-minded way. Okay, can we say more about the presence or the existence of, or why we have it on Earth but not Venus, and whether or not we can expect to have it on other planets for which we can only really see anything about their mass and perhaps their surface conditions? Okay, so can we make this estimate, and sort of hearkening back to the days of giddy optimism, okay, which I guess, you know, today's New York Times makes me feel like maybe we'll go back to that, okay? But we can perhaps generalize, you know, simple damage arguments or simple damage versus healing arguments to other planets to say something useful about it. Now, of course, you have to remember Birch's warning, okay, that you have to take this with several grains of salt. I would also like to acknowledge that this whole problem of understanding whether we have plates on this planet and otherwise, you know, a lot of people are working on this. I mean, people like Adrian Lenardic and Paul Tackley and Doris Brewer. I mean, so it's not just me, but I'm giving you my biased view in terms of interpreting this in terms of damage versus healing. Okay, so we can say a little bit about this. I'm not going to go into all the details, but try to give you at least a flavor. And this is work done by my former student Brad Foley again, that with convection models, we can actually examine whether or not we enter a plate-like state or not. And the plate-like state does depend upon this ratio, or the comparison of damage to healing. The healing dominates, it's very hard to have plate tectonics, and you have a stagnant lid type convection. If damage dominates, you can get softening of the lithosphere and plate-like motion to it. Okay, the healing is surface temperature dependent. So the hotter, much hotter the surface, okay, the healing will be more rapid, and even in the mid lithosphere. Okay, convection, convective vigor, okay, and damage depend upon the size of the planet, effectively through the Rayleigh number. Okay, so the bigger the Rayleigh number, okay, perhaps the bigger the planet, the bigger the Rayleigh number, the more vigorous the convection. So in that case, we can use that relationship between surface temperature and planet size and whatnot to draw a boundary between when stagnant lid and plate-like flow occurs. Okay, that's a function of planet size and surface temperature based through this damage physics, and we find that we can predict. I mean, we sort of arbitrarily put the Earth right at that boundary just as some sort of anchor point. It could go slightly one way or the, well, it has to go at least to the plate tectonic regime, because we know plate tectonics is here, but at least we do wind up predicting that Venus and Mars are about where they're supposed to be. Whether a giant planet, a super Earth, has plate tectonics, it may have plate tectonics if it's bigger, but it may not if it's actually more like a super Venus. Okay, so it does depend upon more things than just the size. Okay, so I've already said all that. Okay, so the last thing I would like to talk about, and I've got a few minutes, is a new problem that I've been working on, which is this issue of what causes rapid changes in plate motion. Okay, we see in several instances, for example, there was a rapid change in plate motion of the Pacific plate about 6 million years ago, perhaps associated with the arrival of the Ontong-Java plateau, thick crust, into the subduction zone, and it's thought that perhaps that triggered, you know, a big change in plate forces that caused a change in plate motion. Even the change in plate motion associated with the Emperor Hawaiian Bend, Okay, it's actually hard to explain from a mantle convective point of view because it's very abrupt. So it's hard to explain from circulation, mantle circulation, because that usually occurs over tens of millions of years, and this is faster than that. So we actually look at this through the idea that slab necking, that something may cause slabs to be detached and dropped off and lost. Okay, and this is not our original idea. People have proposed that slab necking or slab detachment causes a change in plate forces. Okay, and also can maybe cause rapid uplift. Okay, underneath continents. Okay, so we've applied our simple damage theory, I guess not so simple, to this necking model where we say we have a subducting slab, very simple looking slab, dropping off in normal subduction, but if a big chunk of crust, a plateau or chunk of continental crust runs into the subduction zone, it plugs it up. And so that upward plugging motion kind of is opposite the downward pull of the weight of the slab, and it causes it to neck. And the necking can be accelerated by this grain damage physics that we have been talking about. So in this case, we have a force balance. Basically, it's the necking stress is holding the slab up, and there's support from the viscous flow of the mantle, which is this beta, basically represents the viscosity of the mantle. The rate that it necks is just basically the rheology. It's a strain rate in the necking region is a combination of dislocation diffusion creep, and that diffusion creep depends upon basically effectively like the grain size, okay, and it's governed by this competition between healing and damage. Okay? And we can put all these things together, okay, and do a very simple calculation. Okay, I'm actually supposed to, and you saw on the previous slide, I was told yesterday required to say this is embargoed. So it's a big secret between all of us, okay? All 1,200 of us, don't tell anybody, yeah. Okay, so this is in press and PNAS, I guess, and embargoed. So now you heard it. Okay, so if we actually look at the results of this, one thing we see at the slab next, the lower portion of the slab drops off in about a million years. If the plug, the chunk of thicker crust, plugs up the subduction zone if it's thick enough. If it's too thin, of course you expect it to undergo normal subduction if it's like normal oceanic crust, but if it's thick enough, about 20 to 40 or so kilometers thick, it can cause a slab necking, and the slab necking can occur in about a million years or a couple of million years if the damage is high enough. And also importantly, we look at the stress, okay, that if there's no damage, the stress of even the necking slab doesn't actually go away and continues to pull down. But with damage, that stress basically collapses. That stress can go away, okay, with a high enough damage in the order of a million years or a few million years, which means that we've just lost the pulling force of the slab very abruptly, okay, and that may allow for the rapid loss of the slab pull force that would then cause an abrupt change in plate motion or even in uplift. Okay, so in summary, which you probably don't need to see, but in summary, we've sort of explained very quickly the grain damage mechanism, and it's built from basic physics, and it's basically consistent with experiments and field observations. Like I said, we could always do better, okay? But it seems to allow this generation of tectonic plates with Earth-like conditions, okay? The emergence of these plates over this billion years may be explained by damage accumulating, okay, in this way, and being inherited to form passive boundaries. Okay, on Venus, the damaged weak zones can't accumulate; it just the healing just dominates. And in planetary tectonics, okay, it does depend on size, but also on surface conditions, which are, of course, are the few things that we can measure. And abrupt tectonics from this rapid slab detachment, may be explained by the same physics that we've been talking about. And I do want to thank at the end my collaborators, okay. That have worked on this with me, various components of this, especially Yannick Ricard, who I've been working with for many years, my student Brad Foley, Billy Landit, one of my more distant students who actually really started a lot of this question of tectonics and climate, and of course Jerry Schubert, and I of course need to acknowledge NSF for patiently funding this for all these years. And thank you very much.
So if you ask a question, which I hope you do, there's microphones available for you to come up and ask questions so everyone can hear you. So
I can see you. You believe this? My goodness. Okay, right?
here's the wrong.
Aha. Okay.
Hey, Dave.
Is it working?
Yes, it is.
Okay.
So there's another place where plate tectonic doesn't work quite as well as what you've shown there, which are the continents of the Earth.
Say that again.
The continents. The continental crust often is thought to have less plate tectonic-like behavior, although not completely absent, right? And so, but it has the same temperature, and therefore the healing should be the same as it does in the ocean. So what do you think is the difference there?
So what's the question? Why don't we have what? I mean, why?
Why is the plate tectonic regime not as well developed in the continents as it is in the oceans?
Oh, I see what you're saying. I mean, the continents do undergo sort of continuous deformation. I mean, in the continental crust, it's gooier and softer, and it tends to spread more. So they don't, you know, if they're not always being shoved together, they tend to spread apart, okay, because they're generally weaker. You know, I'm not so certain that they don't. I mean, obviously, we have not included continents, okay, in this problem. But, you know, if you have thicker continental crust, you have depleted continental lithosphere that's ostensibly stronger, okay, by being dehydrated, as Greg has shown before. So there may be, you know, there are all types of other levels of complexity, but those would be probably the first thing that I would answer with.
Audience right over here. Way to the right.
Okay, I see one of my old grad students. Okay. Oh, way over there.
Way over here. Sorry.
Way over there. Go for it. Okay.
Mine's close to, similar to the question. When we look at Phanerozoic rift systems, they tend to break up in places where we see that the continental crust is thick. So we have the weak continental crust replacing the strong mantle. So those of us looking at Phanerozoic rift systems have gone back to this pre-weakening of continental crust, and I really think that fundamentally the bimodal composition of our lithosphere is an important part of this development of plate tectonics. And I wonder if you could comment on that, because these don't have anything to do with grain sizes or anything like that.
No, that's true. And sort of the contrast, like you said, between continental and oceanic lithosphere in particular, I mean, that would certainly cause some focusing of stress. Okay, but you have to sustain it. Okay, in other words, you have to continue to focus it down to develop something like a plate boundary. Okay, I mean, there's oftentimes, you know, intrinsic heterogeneities like this that may wind up causing, you know, some breakup or some inhomogeneous deformation, but you have to continue to focus it down to get something that starts to look like a plate boundary. So we're always looking for these feedbacks that allow the weak zones to become narrowed and sustained. Okay, so I think it's, you know, there's no doubt there's heterogeneities, even as Laurent pointed out, okay, that we're not dealing with, but we're really looking at for where these focusing feedbacks are. I'm not sure that answers, but I tried, okay. There was some, okay. Hi, Magali.
So I would like to hear a little bit more about the other mechanisms that can cause or contribute to damage. I'm thinking of things like water and melt, and in particular the question related to your diagram of where you have plate tectonics, what kind of planets you have plate tectonics on and what planets you don't. What you showed seemed to be just related to sort of grain size and temperature. What is the role of fluids in terms of where you're going to find plate tectonics and what planets?
Well, I mean, taking our various models, you know, and interpreting them to try to answer that, okay, we would argue and have argued that the role of water in this case is not actually to be ingested and soften things up, okay, but to provide to support the carbon cycle that winds up keeping the surface temperature down, okay, and so the role of water is to mitigate the climate, okay, and keep it cool enough to allow for damage to be more important than healing, okay. And one of the arguments we've made, actually based on Greg's work, okay, is that the lithosphere, okay, most of the lithosphere actually tends to be pretty dry because of melting in mid-ocean ridges. So we're trying to explain this without trying to ingest water to great depths, because we have to actually support plate boundaries, you know, not over 10 kilometers, over 100 kilometers or so, okay. So the problem is we're doing it in something that's already probably a pretty dry lithosphere.
So you would say that actually for planets, it's not as important.
No, I would say that it's important in that the water, if it's supporting a carbon cycle, it's suppressing the surface temperature. That's how we would interpret that model. Of course, you know, that's a very one-sided interpretation. I'm sure it's much more complicated than that. Okay.
Yeah. Hey, David. I was just wondering, because this the work with the strike-slip stuff and the stagnant lid on Venus suggested this strong temperature dependence on the healing rate and the damage rate. How deep within the Earth's mantle would you expect that damage could stay a strong, stay ahead of healing?
Well, I mean, we think it can't. I mean, when you go down too deep, okay? So once you're, going up another, I mean, it's almost as if we were saying we're taking the temperatures in the middle lithosphere of the Earth. If you jack the temperature up to something, like you would do to Venus, you're going to have a problem. So if I were going to do the same thing by dropping that damage zone to the deeper mantle and moving the temperature up that way, okay, then we'll probably start losing these damage zones. But even we see this in convection calculations, that the damage doesn't go away entirely in the deeper mantle. We still seem to see some sort of conjugate type weak zones, even in these subducting slabs, even as they go down a few hundred kilometers, and then they kind of go away. Okay. Moving around enough to keep the cameraman busy. Okay. Okay.
Hey.
Hi, Anwar.
So we see those myelonites, like to go from an equilibrium texture to a myelonitic texture, you need like a large strain.
Right.
And to sustain those large strains, you have to have like some kind of boundary, like there has to be some kind of predefined boundary to like move, like it should move so that that can generate so much of strain, and that could lead to the weakening. So doesn't that seem circular, like?
No, I understand what you're saying. I mean, in our case, the way we would have developed it is, we were starting off with a coarser grain system.
Yes.
Right, but we're trying to drive the grain size down smaller, and it's complicated. Of course, this is why we had to introduce the Zener pinning to try to support that grain reduction. But in the end, if we wind up starting to get that feedback that is positive, then you can start to drive the grain sizes down smaller, at least in the theoretical sense of putting these things in. Even with simple shear zones, we tend to see the shear become more focused.
Yeah, but what causes, like what starts that shear zone? Like you have a...
Well, even if you're starting off with sort of a broad deformation sort of being driven, I mean, even in these calculations with the spinning spheres, you were seeing a lot of the localization, or the original localized deformation was just occurring because we were dripping off a slab. Okay, yes. Right underneath it. That caused a weak zone that then, as it got inherited to become a shear zone somewhere else, it became even more focused as it continued to deform. So there was some, it had to be nucleated by a slab somewhere at some point in the past, at least according to those models. Okay, sure.
All right, everybody, let's thank Dave again for a great talk.
Okay, thank you.